All right, so we want to continue our discussion about how we deal with reactions that are approaching equilibrium. And so the first thing we need to do is be able to predict reaction direction. And we can do this by looking at a value called Q, which stands for the reaction quotient. The reaction quotient has the same form as K, but doesn't have to be at equilibrium. All this means is that as we proceed, we'll calculate Q the same way we calculate K. If we know K, we can then make comparisons between Q and K and decide on the system or state of the system. And so when looking at Q versus K, the following things can be known. If Q happens to be equal to K, then we are already at equilibrium. We've reached a free energy minimum. All reaction rates are proceeding forward and backward at the same rate. If I look and see that Q is less than K, because of the way Q and K are calculated, that means that I have too many reactants and I will make more products. Essentially, the way K is calculated, if you remember, is products divided by reactants. So if I have products divided by reactants being too small, then I need to convert some of my products some of my reactants into products to make that number on top smaller and the number on top bigger and the number on bottom smaller, both of which will cause the value of Q to increase. And then finally, if Q is greater than K, I have produced too much products, and I need to go back and make reactants. So I need to convert some of the top of my fraction back into the things on the bottom so that I have a smaller number on top being divided by a larger number. Both of those things lead to a reduction in the size of Q. And so how do we deal with this? Well, we can take an example here where we have at 448 degrees Celsius a reaction between H2 and I2 to make 2HI. And we're going to know that Kc for this reaction is 50.5. And we want to know in what direction the reaction will proceed if we start with the following concentrations of the components. So I'm going to put in a little product, a little of each of the reactants, and we want to see what will happen. So since we don't know if this system is at equilibrium or not, we're going to start by calculating Q. That's our snapshot for K. And for this reaction, since everything's in the gas phase, Q should equal the concentration of HI squared divided by the concentration of H2 times the concentration of I2. And so now we just need to enter those numbers. According to this, the concentration of HI is 2 times 10 to the minus 2. So we're going to take 2 times 10 to the minus 2, and we're going to square that. That's going to be divided by the concentration of H2 times the concentration of I2. H2 is 1 times 10 to the minus 2, and I2 is 3 times 10 to the minus 2. And all of these are in a 2-liter container, so essentially all of these must be divided by 2 because they don't give me concentrations up here. They give me moles, and they give me the volume of the container. So I'm going to divide everything by 2 in order to have molarity. And this is inclusive. This 2, it means divide this entire amount, then do any squaring or whatever else we need to do. Okay, and if we do that, we'll see that Q happens to be 1.33 bar. So 1.33 repeating. And so if we want to compare Q and K, we know that Q equals 1.33 while K equals 50.5. So we have a situation where Q is less than K. And so we know that when Q is less than K, we need to proceed towards products. So we proceed to products. We need that value to be bigger, so we need a bigger number on top, smaller number on bottom. And when we say products, we're generally saying right. You'll hear me say that a lot. Proceeds to the right, proceeds to the left. That's what I'm talking about, to the right side of the reaction arrows. Okay, so how then do we know what units to use on K? because I know when we use the lowercase k, our small k referring to kinetics, we always were very interested in the units. Well, for equilibrium k, KEQ, k is unitless. You might ask how? It's got concentrations and pressures and all those things inside it. Well, as it turns out, all those concentrations and pressures are made relative to the reference values for standard conditions. So all pressures are relative to 1 atmosphere or 101.3 kilopascals, depending on the unit you're using, and all concentrations are relative to 1 molar. So since every value has been divided by a standard, none of them have any units, and so that lets us work with a K that has no units. And so that makes our life a lot easier. We don't have to worry about units for K. It's just a reference value that helps us understand the state of a system at any given point in time. And so that ends our simple discussion of equilibrium. The next lecture will begin talking about more complicated aspects of this process.